Great. Thank you so much for joining me today. My name is Tarek Mehrez, and today I'm going to talk about Python's concurrency model in the web. It doesn't really come as a surprise, I think, when we think that Python is not the fastest in terms of execution time. And I think last talk we've also seen some tricks on how we can make sure that it runs much faster in a single core. And throughout this talk, I'd like to expand a bit on this topic. So how can we even speed up things a bit more by having some sort of concurrency? We'll explore a bit of parallelism, but I think concurrency is the main aspect here. Now, one main assumption, obviously, your favorite service will run on some platform, such as Kubernetes or some serverless in your cloud provider, and they kind of do the horizontal scaling for you. And that's not really what we're interested in here. I'm kind of talking about the basic compute unit, which is running in Python. How can we speed this even further within your container, within your process? So if there's one thing I would love to get out of this talk, it's what are the options out there? So if we're exploring different possibilities, again, for deploying web services in the cloud, on the web, whatever, what are the options so that we can speed up our deployment? We can make sure that the service is much more resilient. And by resilient, I mean we can take more traffic without worrying about reaching limitations in terms of worker nodes, in terms of CPUs, and so on. So this is sort of what we're going to explore today. But first, a bit about myself. My name is Tarek, or Tarek, if you're not an Arabic speaker. Originally, I'm from Egypt, and currently based in Amsterdam for the past 6 years. And I work for a company called Klarna. So Klarna is arguably one of the biggest fintechs in Europe and the world. We're mostly associated with the buy now, pay later aspect. So if you're shopping with your favorite e-commerce website, probably you've seen Klarna as a payment method, but we're doing all sorts of other things, such as like banking. We have cards in different markets, and we're operating across the globe. We also have engineering hubs all over Europe, so if you're interested, feel free to reach out to me if you'd like to join. But yeah, now we can go back to Python. And one disclaimer, this is not necessarily related to the work we do at Klarna. It was sort of my personal experiences throughout the years with how do I kind of navigate the issues I'm seeing when it comes to deploying Python services in the web. So what are the options? What would we would like to explore? And I think these are sort of the three main aspects that comes to mind. So multiprocessing, you achieve parallelism by having multiple processes, whether through Gunicorn or just manually by saying import multiprocessing, and you spawn multiple processes. So this is one aspect or one way of doing things. Gevent, I think, is also very interesting in how it achieves concurrency, and I will kind of just have a tiny dip into Gevent and how it achieves concurrency within web frameworks, and specifically Gunicorn. And then last but not least, async I/O. And I think this is the most interesting mention, because recently when it got into the standard lib, a lot of new technologies or frameworks have emerged that supports this natively. And this is what I would like to explore as well. So basically, we'll be exploring or comparing these three in the web aspect. So again, this is mainly about the comparison, but it's not really about deep diving into one of these. So we'll just, as I mentioned, talk a bit about the event loop, how async I/O works, how do you kind of change your code from sequential synchronous execution into async execution so that you can achieve this sort of concurrency. But we're not really deep diving into any of them. And I think it's also kind of ridiculous to say this framework is amazing, this framework is bad. Depends on what works for you. All right, before that, I'd like to tell you a very quick story about my very first Python service that I wrote. So I think 6 years ago, a data scientist that was working for me on the same team came in and said, we have this machine learning model. We'd like to deploy this behind an API. So have /predict, I give you some strings, you give me back some entities. So basic NLP, basic information extraction. So naturally, I used Flask, because it's a very simple way of doing things. You just have your dependencies in there, you annotate your function with the endpoint, and you're good to go, right? And it's very simple to deploy as well, or run, not deploy, because it's as simple as, well, Flask run, and you have a dev server running, and we're good to go. What is the issue here? It's a single thread, single process server. That doesn't work, for the very simple reason that your worker or the process, and I think this is the baseline that we start from, is blocked. It is waiting for this request. Specifically, it's CPU intensive, since it's a machine learning model written in Tiano. I think TensorFlow was still in beta back then, so this thing took like 3 seconds to execute. Imagine sending 10 requests at a time. So most probably they will just time out. So this was the issue, and we need to do better in terms of that. So how can I put this thing, how can I change this dev server into some better server, web server, that I can put in production behind the container? And then Gunicorn, oh yeah, we can do better. And then Gunicorn came as a natural decision. So this is where we start with the first option, which is multiprocessing. What does multiprocessing achieve? You still have Flask as a web framework, still synchronous code, nothing changes in your code, but instead of deploying this behind the Flask dev server, you can use Gunicorn. What is Gunicorn? So Gunicorn simply is a Python web server that provides some capabilities which people can use in production to make sure that your service is actually resilient. And in that case, we have a pre-fork server. So pre-fork means we have pre-forked processes that can take in your requests. So in that case, if I say, I need 10 processes that would listen on this port and take in requests. So essentially what happens here, Gunicorn tries to achieve this by spawning 10 processes, and I'm talking OS processes, which are obviously expensive, so that's a downside. And then you say, okay, then I can take much more than one request. And that doesn't really run on its own just fine. We need something else. So we need something like Nginx. Why? Because at the end of the day, Gunicorn is still blocking. So even if I have 10 processes instead of one, I'm still waiting for work to be done before I can take in the new request. And that's kind of a bottleneck, that's an issue. And Nginx usually provides more or less an asynchronous way to deal with this. So Nginx can take multiple requests at a time, send it over to Gunicorn so that you can handle slow clients, so that, I don't know, if you have one of the clients would wait for like 2 minutes, you don't block the entire service. You can still do more stuff. But this is what Nginx provides. The takeaway from this slide is synchronous processes on Gunicorn are still a bottleneck, and that's still an issue. So we did slightly better, but it's not great. It's not good enough. So how many requests can we take at this point? Definitely more than one, because we have multiple processes. Nginx does some buffering for us. So with a specific factor, we can assume that it's as many as the number of processes we have. And some people are, actually most people, including myself at the beginning, I thought, okay, this is good enough. If I have 10 processes working, I can just use Kubernetes, scale horizontally, have 3 pods or whatever replicas running, and I'm good to go. How many do I need anyway? How many requests do I need anyway? Well, you will be surprised. If that is synchronous and that's running on a bigger system, waiting for even more APIs that they're blocking on them, this kind of doesn't work. So the whole thing when it comes to scale becomes really an issue. A deeper look into Gunicorn, and I think this is mainly a visual attempt to describe what I've been talking about so far. So as I mentioned, we have one master and workers. The master has one job only, which is to make sure that your desired amount of workers are up and running. So if any of them are killed, you kind of restart the process. And if you use Gunicorn before, you would see something like starting Gunicorn, starting processes, blah, 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 and then you listen on the port and the network interface, and hence the term pre-fork, because you do this before the service starts. There are other models that I'm not really getting into that you can fork while the service is running, so maybe one per process, that will be very expensive, or maybe have a pool which you fork every time you have a specific amount of requests so that you can handle spikes. So there are different models or different ways of handling this. And the workers get the HTTP request directly. One thing which is not necessarily part of this slide is the WSGI interface, WSGI, and that's something I would like to touch upon very quick. Maybe this is even a better slide. So we need an interface between HTTP and Python. Python, at the end of the day, is a callable. You call your function, but you don't really pass HTTP info. Python is not aware of that. So the WSGI is essentially an interface, a mapping between the Gunicorn, which is the web server, into your callable, which is the Flask callable in this case, or can be Django, can be whatever web framework you would like to use. And again, WSGI is synchronous because everything in this process or in this flow is synchronous. And keep this in mind, this will be useful afterwards. All right, so as I mentioned, the workers are synchronous, and we'd like to do better. So Gunicorn has an amazing feature that not all workers have to be synchronous. You can actually have async workers. So how do I have async workers if my code is synchronous? There's no async await, there's nothing. No import async IO, just my code. But then Gunicorn will have this async aspect. How does this work? That's something that we will explore right now. But before then, would like just to have a very quick intro on what async actually means. All right, so async execution. You have a Python function. You turn this into a coroutine, and we'll talk about this now. So different async frameworks it's just def, do something, takes parameters. That's your function, right? The moment you put async behind, it becomes a coroutine. And at least that's how async IO does it. Some other, like Gevent, for example, they call it greenlets, and it's essentially the same concept. Coroutines get scheduled as a task, and then there's an event loop. Literally a while true running, if you check the source code, that checks which tasks or coroutines are now ready for execution, and these get executed. Why aren't all of them ready for execution? Because I might be waiting for an API, or I'm writing something on disk, or I'm waiting for a database connection to be done, like a request from the database. While this coroutines, or essentially function, doing this thing, other functions can also execute, and that's basically what the event loop is doing. So it's sort of a tiny scheduler within the Python process. And again, all of this is still single process, single thread. And that's how we're achieving concurrency here. So ideally, we would love to take this model into the web, into the API that we're currently building. So again, make it even more visual, assuming that these are the threads or the coroutines. They're not actually threads. The coroutines and the event loop is choosing who to execute next based on which coroutines are ready. Now there's the notion of cooperative multitasking. Sometimes in some models or some implementations of not async IO, but I think others would say, I'm done. I executed long enough. I will yield or give up the execution flow for another coroutine to take on and do stuff. And that's the cooperative aspect. I'm not entirely sure if async IO can do that, but Gevent, for example, can definitely do that. So halfway through the function, you can say, give the execution flow to someone else. I'm expecting this to take so long. Most likely, if you're implementing an API, you don't really care about all of this, but it's still good to know in case your implementation is CPU intensive or you're doing something which IO that takes long time. All right. Back to Gevent. So now we know what the async execution is about. Can we take Gevent as it is or as a framework to do this within the web? Very quick background. Gevent was a really nice attempt to implement all of this within Python before async IO was part of the standard library. And Gonicorn thought, well, I can take this as part of my workers. You will still write Flask, you will still write Django, but I will try to replace the sequential, the blocking flow or execution into an asynchronous one using Gevent. And we will get to that in a bit. So yeah, as a Gonicorn worker, that's a very important aspect. All right, so each worker, remember the 10 workers or the n workers that we had? Before they were synchronous. Now they're no longer synchronous. Now they're async by having the Gevent servers in place. And it has its own event loop implementation, runs on libev. I believe libev is also the implementation behind the Node.js event loop. So it's not really, now there is, as part of the standard library, the Python event loop. This is different, that's a different one. And now we've achieved the non-blocking aspect. So it's exactly the same slide, right? Nothing has changed. The only thing that changed is the Gonicorn worker, as I mentioned before. How does this happen? Something called monkey patching. So Gonicorn gives Gevent the capability of changing the Python functions that you have in your Flask or Django code, and during runtime, it tries to make sure, or tries to make them async, basically, by monkey patching the execution. Now, that's a really nice idea, but it's also quite opaque. If I'm changing the runtime from sync to async without me changing the code, things can definitely go south. So from a usability perspective, and there's literally a blog post called Monkey Patch and Pray, because you hope that this thing will just work. I do remember then that on Flask, it actually did work on the machine learning service. So I said, OK, Gonicorn, I need 5 workers of type Gevent, and it did have this async thing work. I tried this with Django. That didn't work because some of the ORMs and the database drivers just did not like that, and debugging was so hard. So it's sort of a pseudo async way to do things. Now, this does not mean that Gevent is bad. You can still write your entire piece of code in Gevent using their own functions, and that works just fine. The part which gets a bit hairy is including this in your Flask or Django implementation. But now we can have much more incoming requests than the workers. Now we're no longer bound by 10 requests in parallel because this is what the synchronous worker can do, which is an achievement, I would say. That's good. But we can still do better. So as I mentioned again, Gevent monkey patches the synchronous code to achieve this async execution, with the downside that it just won't always work. All right. What do we have so far? Fully sync, what I call pseudo-async, with the Gevent worker. Cool. We can still do better. Async I/O. So finally, we have async I/O, and it essentially, after lots of peps and lots of ways trying to put this as part of the standard lib, async I/O is part of the standard lib, great. And then new kind of web technologies emerged out of this. We thought, okay, instead of just Flask and Django and their likes, we can have now async web frameworks such as Starlet and FastAPI. Instead of the WSGI, which was the synchronous mapper from HTTP to the Python callable, as we called it, so this mapping to the web framework, we can now have ASGI, which is the asynchronous way of doing this. And this also enabled things like long polling and WebSockets and so on in a much more efficient way, which is really nice. So for the rest of the presentation, I'd like to explore a bit what async I/O actually added. But let's go back to how we defined the async execution. So again, same exact idea that functions become coroutines. But in that case, instead of using Gevent with the monkey patching, we're just typing async. So before the definition of the function, you say async dev do stuff. And then it becomes a coroutine. And then what happens? This coroutine becomes a part of the event loop, which is something we're interested in. Now, something to keep in mind, if you have blocking code, not everything can be async, right? There will always be this dependency that has to be blocking, that you cannot just execute this in an async manner. Your code will be as slow as this blocking part. So it's not entirely magic, right? So, and this is also something to keep in mind. So if this thing exists, if this blocking code exists, there's nothing to be done about that. Maybe you can offload this to some other parts of the system, do it offline, whatever. But keep in mind that this doesn't speed up this part. This part remains as is. And yeah, as I mentioned, there are multiple implementations of the event loop, and there's one already which is part of the Python standard lib. Why do we care? Because now, instead of relying on external frameworks, such as Gevent, we can now have this as part of the actual Python code or Python standard lib. And this means that you can add more dependencies, you can rely on more stuff without worrying about, will the monkey patch work? Can I unit test this properly? Is there something that might go just break and without us knowing about? And this is something which is really interesting. And again, no need for monkey patching, so that's also good. So what do we have so far? As a quick comparison. We have Flask, Django, and FastAPI or Starlet. It could be much more stuff. It doesn't have to be only these frameworks, of course. Instead of Gunicorn, there is now a UVicorn, which is also a web server, also written in Python, and now it sort of supports the ASGI in a native manner. Whether you need Nginx or not, that is an open question, because one might argue, well, I'm already async. Do I need this slow client handling? Maybe that's not necessary, but it also supports stuff like SSL termination and so on. So if you're really putting this as part of a bigger system, you might still need Nginx. Now, there's another plot twist that Gunicorn does support UVicorn workers. So remember the Gevent workers, they're also UVicorn workers, so that you can start multiple workers, as we said before. So we have N workers running, but then they're all natively async. They're all running the UVicorn processes. The downside of this is you don't really share the event loop. So now you have 10 parallel event loops running, which is maybe something you're interested in. If they're not sharing a state and you're having this behind an API, maybe that's great. And some comparison that I wanted to do. So this was also part of me trying to ease it out for myself. If I'm choosing which way to go, what might be an interesting or a good setup to go with. So with the multiprocessing, as we said before, it's purely synchronous. You're writing synchronous code. There's no async, there's no await, there's no mapping, there's no whatever, just synchronous code. Gevent, you're not writing synchronous code, but the execution is somewhat async if it does work. And async I/O is inherently async in both the actual code that you write. So if someone is not familiar with the keywords and sees the code, I'm like, I have no idea what this is about. And the execution is inherently async. In terms of debugging, I think it was a bit unfair to say that async I/O is easy to debug, because there will be a lot of things that might happen with database connections, with Redis connections, with unit testing, that you realize, okay, this is not really as easy as I thought. At least it's not opaque, because there's no, again, the monkey patching. At least I can see what's happening. I can see where the async bit is, but I wouldn't go as far as saying that it's easy to debug. And in the latter two options, we actually achieved concurrency. And what does that mean? It means that we can send much more requests than a single process and a single thread can handle. And I think this does matter in a scalable system. Are these the only options or frameworks? Absolutely not. There are multiple, like tons of them. There's Tornado, there's Twisted, there's Trio. I think if you go through, again, the history of how this evolved, you realize that there are multiple ways of doing the same exact thing. The only difference is how mainstream is it? So if you're stuck, can you actually go in there and try to debug things and find support or not? And the other aspect is, what sort of special use case do you have? And talking about the web, I think that's pretty much a standard use case. So going with the more mainstream options is probably an easier way to be able to find this sort of support. I think recently Tornado, because I also mentioned that I will talk about Tornado, I think recently Tornado does support the async await, so the standard lib functionality, instead of before then it was using decorators to transform these functions into coroutines. And again, different framework, same exact abstract concept, function, coroutine, event loop. And now it also supports web, I think it always did actually, web requests. So you can have an API written in Tornado. People seem to be walking or moving towards Starlet and FastAPI for different reasons. But yeah, if you feel like this is a better use case for yourself, then please go for it. One last plot twist. We kind of excluded Flask and Django completely from the async implementation. That is no longer the case, because in new versions, they are supporting async natively. I think with Django, there's a limitation that you cannot go to the ORM layer. So you can do this on a more in CPU and on the API layer, but then once you go to the ORM, probably this doesn't work anymore. So I'm curious to see how this will evolve, because if that actually works end-to-end, and then you have ASGI instead of WSGI, you have something like UVcorn running on Gunicorn, then there's a very big chance that the competition against Starlet and FastAPI, for example, will be quite interesting or quite tough. And Flask is also taking off. So Flask is trying to keep up with this. I think in 2.0, async is currently supported. So this entire comparison saying that this is synchronous and this is async, I think maybe in less than a year, probably be obsolete already. So that would be interesting to see. And that's it. I hope this was helpful. Thank you for your attention.
So thank you very much for your talk. I found personally very interesting. So since we have a lot of time left, we'll be able to go over a lot of questions. But first, let's go over the Slido questions. So the first question is, do you have any tips for error handling in async code?
What kind of error handling? That's, I think, but probably not sure the person is here.
Well, in general.
Clarify. So the good thing about FastAPI, for example, that it shields you from a lot of things. So they kind of wrap responses. So whether it's a serialization issue, whether it's, I don't know, issue with the actual execution, it does give you a better understanding of errors. Something that I kind of went through, and it was quite annoying, doing something like celery, so trying to attach celery on the same event loop, for example. The moment you go beyond the simple use case, things can go quite wild. And I wouldn't have a specific recommendation per se, but try to keep things as transparent as possible. But yeah, I think that's quite a generic answer as well.
All right, so the next question is, did you also run in blocking requests if you use async I/O with background tasks and middleware?
Yes.
If so, how did you solve it?
FastAPI has a beautiful thing called background jobs. So you can just say, run this in the background. And then it gets attached to the event loop, and then you're no longer blocking, which is amazing. Or you can spawn a salary. If you're using salary, you can spawn a salary job, or yeah, that does that for you.
All right, then the next question is, what could be the future? GIL-free multi-threaded async IO loops, or?
I don't think I have anything to say about that.
All right, then let's move on to the next question. So the next question is, do you have any recommendations for wrapping CPU-bound work in an async function?
No, I wish I did. I think background jobs is good. You can do this as a background job. I think the good thing about salary is that you take it completely out of this process and you put it in a completely different process. So that's always good. It depends on how real-time you want to be, because if it's that CPU intensive and you want to be as real-time, probably Python is not even a good choice in the first place. And not obviously as a language you can do better, but also you can use something like, I don't know, Apache Flink to do this intensive computation for you. So I wouldn't really rely on Python, to be honest, if salary is not a good enough job.
All right, let's have another question. So have you used any async ORMs? Which ones, and how was the experience against, for example, Django, ORM, or SQLAlchemy?
So there is a nice wrapper called databases that wraps SQL Alchemy. And you can use this to write async code with your ORM. That worked just fine. The only issue was testing it. So with testing, we use the sync one, but in prod, like in the actual service, we use the async one to have predictability basically on the execution. I think that worked fine. It was sort of a hack, but I think it worked fine.
All right, let's do another one. So have you ran stress tests or benchmarks? What use cases profited and by how much?
Yes, I did a lot. This was the main comparison between FastAPI and Django. So the use case was we had a customer-facing API talking to another API. And the first one was a Django. So if all of the workers were busy talking to the other API, no one was talking to the customer-facing API was blocked, essentially. And this caused lots of problems. So yes, we did lots of load testing, comparing both, so the sync and async. The async was much slower, and the timeouts are slower, but at least it did not fail. And this was good enough for our use case. The problem with Django was you didn't have available, it would just return back an error code telling you, like, I have no workers to serve you. So yes, it will be much resilient, but also a bit slower. And then you rely on CPU, for example, and latency time to scale horizontally, but at least you're still available.
All right, so let's give some more time for the Slido people to write their questions. So does the audience have anything they want to ask, or? Well then, let's move on to the next Slido questions. Well, I mean, a lot of people, they just type their questions in Slido, right? So how do you deal with async code getting ugly or unreadable really quickly?
It depends on how deep you get, I think, into async IO. If you're using, again, a framework, you don't really tap into the event loop and scheduling tasks and timing out tasks and so on. So that's fine. The code is not really ugly. If you want to tap into that, it will get ugly, and then it's up to you to make it pretty. But I think for the basic web use case, it's not really that bad. I think there's a question over there.
All right, sure.
Hi, great talk, thank you. You mentioned the background tasks that you can give a request to work in the background while you have answered something. Is it also possible to have if you have more than one background job asynchronously running at the same time, that they share memory so that these background jobs have knowledge of each other?
I would say doing this within the Unicorn or the web server processes is probably not a good idea, unless you have an external, so it depends. If it's a data structure within Python itself, probably it will get a bit messy. If you're using an external storage system, I don't know, something like Redis, then probably you can do some sort of coordination between both tasks, but you cannot assume that they will run on the same process.
Okay, thank you. Because the question was for inside Python. If you give it to the outside, of course you can share memory. But
Because, I mean, if they're in the same process, they can share some sort of global state. That's perfectly fine, as long as you're not changing it. If you're changing it, probably
so the background tasks don't die after the one is finished, then there would be they could just use total globals of FastAPI then.
Short answer, I don't know. If I get to speculate, probably it will have its own timeout on the event loop itself. So if a task gets scheduled, it will have a timeout. So that it doesn't keep, I don't know, if it takes 6 hours, probably that's not a good idea. So if it times out and it's not done yet, you will not be notified. And that's why Celery is good, because Celery has a proper, like Airflow, for example, you have a proper execution time, what succeeded, what failed, how long did it take, and so on. Yeah.
All right, any more hands? Questions in the audience? All right, then let's move to the Slido questions. So another one is, how long does it take to calculate prediction? If longer than a few seconds, how would you overcome this problem?
By having a callback, maybe that's an option. So you have an endpoint saying predict, and then you do nothing, and then some endpoint either have a callback that gives you back the prediction, or you wait a bit and then consume, I don't know, depends on your system, of course. But separating it into multiple calls is probably an easier way to go. Or just don't use deep learning.
All right, then we move on to this question. So which number of Unicorn workers for G-Unicorn would you recommend? 1 per CPU core, or?
I think there's an equation in the documentation, like workers times 2 plus 1, something like that. I have no idea what this is the science behind it, but I think it's also sort of an art. You cannot really come up with one answer for this question, because if you have 2 CPUs and 10 workers, they will compete for the CPUs, and you end up slowing down your service, actually. It's not a good idea. So doing much more workers than CPUs is definitely a terrible idea. So you just need to keep tuning things until finding something that works for you.
All right, then another question is, do you have a comparison of speed between a sync app and its asynchronous version?
Nope, but I'm sure if you check any framework documentation, they'll tell you we're the fastest. So. I think you need to try it out, I guess.
All right, so another one is, what would I need additionally to get a node WebSockets like setup?
Say again, sorry? Okay.
What would I need additionally to get a node WebSockets like setup?
To get a WebSocket setup. In Django, I don't know. I've only done this in FastAPI, and it's as simple as you define your own endpoint, the same way you do in Flask. You just annotate the function, but instead of having it as an HTTP endpoint, you tell it that this is a WebSocket. And then I think you need to send and receive messages. It's quite simple, actually. It's documented. In the FastAPI, again, I'm assuming FastAPI. Other frameworks, I don't know.
All right, so right now, there are no more Slido questions. However, if anyone wants to continue typing, I can ask a question personally.
Please.
So you mentioned a lot of types of speed-up methods using, for example, Gevent and async IO, stuff like that. Personally, which one did you find the most hard or most difficult to learn by documentation, or like just trying to get it to work, stuff like that?
This is a very personal opinion, but I think the Django REST framework, I just couldn't reason about it. I don't know why. Just didn't make it with me. FastAPI, I do like to have the ability to do things instead of having a very specific convention that I need to follow. And that's probably why people dropped Ruby on Rails at some point. You just fill in the gaps and it works. So FastAPI made the most sense because it was sort of very close to Flask, but at the same time it was async and much faster. So in terms of learning, I think finding one template that you can follow will make things super easy. And it wasn't really an issue about async execution, maybe only with testing. The very first blocker that I had, okay, how do I actually unit test this? And it took me a while to figure it out. But once you figure it out, you can just copy the same template. But with Django, I assume the convention itself just didn't play out well.
All right, so do we have any questions in the audience? Any other hands? Well then, in this case, thank you very much for your talk.
Thank you.